Hi everyone, my name is Pranoti. I'm your host of Under the Microscope, and today we have with us Steve Street, who is a postdoctoral research associate at the University of Victoria in Canada. So, on the left side of Canada, close to the US border. So, hi Steve, how are you?
Hello, pretty good, thanks. Glad to be here.
Let's get started with your research. So, could you please explain your current research at the University of Victoria in super simple words, please?
Yeah, sure. So I work on precision nanomaterials, which is a fancy term for trying to make things that are really small. And so if you think about it in terms of school subjects, you'd be thinking about for example, engineering or design and technology, the smallest machinable size, the smallest size you could 3D print or like laser cut or something. And then separately in science and in chemistry, you'd learn about the molecular world and like atoms and molecules and materials. And nanoscience is the space in between those two sizes. So it's about how you can make things that are too small to machine but too big to be like too big to control via molecules, basically, if that makes sense. And basically, like controlling the shape of stuff in that size regime is really hard because everything wants to be a sphere. So I work on making non-spherical nanomaterials, and the general point of it is we're trying to find out if changing the shape of a nanomaterial can affect its interactions and properties with the world and biology and for a variety of applications.
Okay, all right. So when you say you make materials, so which size range are we talking about here? Are we talking about millimeter, micrometer, nanometer? What are we talking about?
That's good. So we're talking about the nanometers. So some things that are from, so say the smallest particles we make are like 10 nanometers, and then the largest are several microns. So between sort of 10 nanometers and 10 microns is the size that we're working with.
Uh-huh. Okay. And is it because I assume that if you want to make like shapes of, I don't know, a millimeter or let's say centimeter, it's easy to make. They don't become spheres, right? Like everyday materials. Why do you say that the materials tend to be like, why is it so difficult?
Yeah, it's a good question, and I think it's probably because under that scale you can't physically manipulate things yourself, so you have to rely on fundamental physics of how like molecules and like materials interact with each other. And like as far as I'm aware, a sphere is the lowest volume shape, so naturally things want to minimize their volume and their interactions with things that aren't themselves, and so that leads them to make spheres.
Okay, that's like the lowest energy state, and the materials, the molecules or atoms, they try to go to the lowest energy state, which is spherical, and that's why. Okay, so what kind of shapes do you make? Do you make like pyramids or?
Yeah, that's a good question. So I primarily make nanofibers, so things that are quite thin and short. So they have a small cross section, but they're very, very long in one dimension. So we call these one-dimensional materials because that we talk about just like one dimension is a lot bigger than the others. But like our group can make a variety of stuff. So we can also make two-dimensional platelets, which are just like a sheet of paper kind of, but on the nanoscale. So they have like are big in 2 dimensions, but then still really, really like thin. And then there's like not as much research on it, but we're working on 3-dimensional materials as well. So getting the fibers or the platelets to stack together into sort of like arrays and these sorts of things. But there's not too much research on that, but like people have done some work on it.
Okay, so you mainly work on these. Can we call them filler or needles, or what can we call them?
Nanofibers is what we normally call them. Like, yeah.
In real life, like in common people language, what can we call it? Can we call it like hair?
Yeah, like sticks is what I normally say.
Sticks, yeah, yeah. And why do you make them? Two questions. Which material are these sticks, nano sticks made out of? And why do you make sticks? Why don't you make cylinders, for example? Tell me.
Yeah, that's a good question. So we work with polymers. So we work with what we call block copolymers. So polymers are like long chains of big molecules that are made up of lots of repeat units of the same thing. And if you have one polymer chain that has two different what we call blocks, so two different types of molecule that make it up, you can get it to go through a process which is known as self-assembly, which is a bottom-up way of producing nanomaterials. There's two ways of making them. There's like the top-down approach, which is to use something like lithography or to like engineer things really smaller and smaller and smaller. And then there's the chemistry way, which is to build molecules bigger and bigger and bigger. And so self-assembly is this process where molecules will organize themselves into the lowest energy state, and you can control like the properties of that. And there's one interesting thing about people that work in nanomaterials and different like shapes is that everybody uses an analogy with something from the real world. So, for example, like fibers, hairs, sticks, cylinders. And sometimes people use different words, and sometimes there are like subtle differences between them. So the difference between a cylinder and a stick in my mind would be the cross section. So the cross section of a cylinder would be round, and then the cross section of like a fiber or a nanofiber would be like rectangular and that would be down to the chemistry of the polymers you're working with and how they like to assemble.
Okay. So what you mentioned top down, that is something that happens, for example, in semiconductor industry with lithography and all of that. But in real life, if you want to take an example, is if you want to build a building, so top down would mean that you start from the top floor, or not even, you start from like the roof and above that, and then you make it like smaller and smaller, and then you cut it from different sides. So that's like the top down, and bottom up is the foundations, and then first floor, like ground floor, first floor, second floor. That's so what you do is more of the bottom up, which is the ground floor, first floor, second floor, right?
Yeah. So it's kind of like if you're gonna sculpt something, think about it's like a top-down approach would be taking like a block of stone and then chiseling it away until it had the shape of whatever you wanted. Whereas bottom up, which is what we do, would be to just take lumps of clay or something and then mold it and create it into the shape you want rather than removing it.
Right. Yes, that makes sense. So tell me, how did you I'm pretty sure as like a 5 or 6-year-old Steve did not think that he would be sitting in Victoria and making these sticks, nano sticks. How did that happen? Tell me about how did you end up stock in Victoria? Tell me.
Yeah, thanks. So I think as a kid, I always loved playing with Lego. So I was obsessed with Lego, and I used to like building stuff and creating all kinds of things. And I think that kind of theme has continued through my life. It's just that now I work with much smaller Lego bricks. So that's kind of the way I think about it. And I've had an interesting career path that sort of varied a bit, and it's not been standard, I guess, but every step of my career, I've just made the decision which I did what I wanted to enjoy most and what I thought sounded most interesting, and I sort of took advantage of opportunities that presented themselves. So I didn't intend on studying chemistry at university. I was thinking of doing computer science. I went to a couple of open days, and I had a couple of bad experiences with the computer science open days, and then I had a couple of really good people that presented chemistry at the universities, and I thought, oh, this actually sounds quite interesting. I was probably wowed, like a lot of people, by sort of like lasers and explosions and liquid nitrogen and stuff, and I was like, yes, this is cool. I want to study this. And then afterwards, I worked in industry for a bit after my chemistry degree, because at the time I just was looking for all opportunities, and I won an award for being the most improved chemistry student at my undergraduate, and the company that provided that award were the company that they offered me a job afterwards, basically, and I was like, this seems like a good opportunity. So so working.
You had what? Most improved. What does that mean?
Yeah.
That you started with grade 0 and then you went, like, you improved over the course of your undergrad? What does that mean?
Yeah, that's basically what it means. It means someone who had lower grades at the start of their degree and then had better grades at the end. So I think my average every year went up. So I think I started at like 60%, and then in my first year, and then had maybe like 65 in my second year, and in my third year I got like 69.5%. I worked out my average was like 69.5% or whatever it was. It was the highest grade you could get without getting a first, basically. And so I did the maths for like my final year and worked out that if I got like 74% in my final year, I would get a first. So then I was like, okay, I'm committed to doing this in my final year. And so like in my final year, I got like 84% or something. So I tried a lot harder in my final year, and so like I
Oh
won an
my
award.
God, this is so cool. I love the idea. Sorry for interrupting, but I want to take the moment to acknowledge, or rather mention that I love the idea of most improved student, because oftentimes the scholarships or awards or whatever, everything is for like the people who come first, second, or third, maybe fifth, and that's it. But these are usually people who are consistently over the course of their studies are first, second, third, fourth, or fifth. But this is really cool. Oh wow! No wonder you took that job. That's awesome. Okay, sorry. Please go on.
Yeah, so yeah, it was a really good idea, and I think people that like that normally have the most interesting journeys, I guess, because they've had to overcome obstacles and yeah, shown improvement. And whereas if you're always in the front and always best, then you haven't had to overcome as many obstacles, I guess, or yeah. So I worked in this industry job for about a year or so. And it was in agrochem. It was like a contract-based agrochemical company. So my job was literally like weighing soil out and then working out how many what pesticides were in it. So measuring the amount of different pesticides and stuff. And we got to work with quite a lot of different things. So it was kind of interesting, but then also it didn't really challenge me as much as I wanted. And so then I thought about doing a PhD, and yeah, I was lucky to get into the Bristol Chemical Synthesis Centre for Doctoral Training, which was like an amazing opportunity. And so yeah, for people that don't know about them, in the UK they have these things called CDTs, which are centres that specialise in training PhD students in areas that are important for like the economy or whatever. So they pick one particular area, and then it's great as a student because you get to choose the project you want to work on. So there's lots of academics that work with the centre, and you do a few rotations in each lab, and then you get to pick from I think we had about 30 projects that we could choose from, and we got to choose what PhD project we wanted. So it gives the power to you rather than the power being with the academic, which is quite nice.
So yeah, the one choosing.
So I worked on. I was always fascinated by biology and medicine and stuff. So I chose to work with carbohydrate-based anti-cancer drugs, which is a bit yeah, it's very different because at the time I didn't do biology at school, so I knew no biology, just chemistry, and it was quite a steep learning curve for part of my project. But it was I really enjoyed it, and it was really interesting.
So was this like pasta or bread as anti-cancer? Because you said carbs.
Yeah, so we're like sugars basically. So yeah, I was working with glucose. I worked with a couple of sugars, like glucose and mannose, and so yeah, literally like table sugar or so brewer's sugar. If people that brew beer, it's like dextrose or glucose. I was modifying that, and then yeah, attaching it to some molecules that people use in the semiconductor industry, and made these weird, we call them ambiphilic molecules. So they had really weird properties, but I was trying to get them to bind to these special four-stranded DNA structures that are called G quadruplexes, and the G quadruplexes are were known to be overexpressed in a variety of cancers, and so we were trying to stabilize them and then kill the cancer cells.
Did it work? Which kind of cancer? Is it coming to the market? If I eat bread, will I be curing my cancer? Tell me.
I don't think so. These ones were structurally a bit different, but yeah, it's a really interesting area. There are no drugs that currently approved that target G quadruplexes, but there is a couple that are in clinical trials, and yeah, it's a very interesting area.
As a scientist, ethically, I should stop saying eating bread might cure your cancer. I didn't say that. Okay, sorry. Please, your PhD sounds really cool. PhD work. Okay,
Yeah.
Go on. Yeah, I go to PhD. Okay, I got it.
Yeah. So so as part of that, I was trained as a synthetic chemist. So I did rotations in inorganic chemistry and supramolecular chemistry and organic chemistry, and carbohydrate chemistry is organic chemistry. But I also learned I wanted to test the compounds myself as well, because that seemed like one of the most interesting parts. So I did I learned how to grow cells and do the biology side of things myself as well, and that was really fun and rewarding. And so at the end of my PhD, I was sort of thinking about what I wanted to do next, and I thought I really enjoyed working on anti-cancer applications. But I thought the compounds I was making, they were a long way away from being approved and actually solving the problems they were aiming to treat. And so I was thinking about other ways what do I think is most promising for treating cancer and diseases like that. And then at the time I was really interested in CRISPR and nucleic acid medicines and mRNA and stuff like that. But that was in the realms of biology, not chemistry. And so I wasn't sure what I could do to work on that. But then I applied for an EPSRC doctoral prize fellowship, which is an opportunity to conduct your own research in a group in the UK. And so I joined the group of like Ian Manners to work on polymer-based delivery systems, because I thought that I read a couple of articles about how the delivery of medicines was a big challenge, and I thought that's something that is in the realms of chemistry, and that's something that chemists can work on. And yeah, so that's the group that I'm still in today now. So I've sort of several years down the road into the journey of working on these systems.
Oh wow. Oh, so that's what you're doing right now. So that's what was it? What fellowship is that?
It's called an EPSRC doctoral prize fellowship. So yeah, that was for 2 years. When that finished, I at that point my supervisor, his group was in the University of Bristol in the UK, and then while I was there, he decided to move his group to the University of Victoria in Canada. And so towards the end of my EPSRC fellowship, I had the opportunity. He said, "Would you like to come to Canada and do research over here?" And I was like, "Yes, this sounds like an amazing opportunity. I would love to visit Canada and see what life is like there." And my projects, I hadn't finished like a few of the projects I was working on, and so I wanted to take the opportunity to sort of complete what I'd been working on.
Oh, so how long have you been in Canada?
So I've been in Canada for about 3 years now, I think. So I arrived just before the pandemic.
I think you made the right decision. Spending the pandemic or being in Canada during the pandemic instead of in the UK. Sorry, but they made some shitty choices. I'm not sure. Okay, but that's really cool. Wow, from someone who was interested in working on Legos. I think your research came kind of full circle. Like now you're also doing the same thing, like bottom up sort of a thing. That is really cool. So, I mean, honestly, your research journey is super fascinating and super interesting. And I have so many questions for you about your PhD work, about your postdoc, about everything. But I'm going to stop myself and ask you this. And this is a tough question, okay? If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one and explain it to us in simple words in the section we call In Other Words?
Yeah. So I think I would pick I told you that I worked on like tiny sticks, as we call them, and the area that I'm most interested in applying them to is nanomedicine. So we want to try and use them as tiny delivery systems to deliver medicine inside the body, which is a big challenge because getting medicines to the right location is quite hard. And that's for example one of the reasons why like brain cancer is much harder to treat than if you had, say, a blood cancer or liver cancer or something like that. It's much harder to get medicines into the brain to treat the disease. And so basically, I make these tiny sticks and I functionalized them and gave them the ability to complex DNA so they could carry nucleic acid cargo. And yeah, so there's a few people use polymers for delivering DNA, and that's like quite a known thing. And recently people have developed what they call microplexes, which are self-assembled polymer nanoparticles that carry DNA. But normally when people carry DNA, they put DNA in the center of a nanoparticle where it's protected. But in microplexes, they're on the outside of the DNA, so they're on the outside of the particle. So you can think like a good way to think about these tiny sticks would be like a hairbrush, for example. So you've got like the backbone of the hairbrush is like the core of the nanofiber or the particle, and the bristles are the corona, or what we call the outside part, which is what makes it dissolve in water and what makes it self-assemble. And what I developed was these particles that can bind like DNA sequences to the outside. So it's kind of like hair getting stuck in the hairbrush. It's like that, except on a nanoscale, and it can deliver the hair as a medicine rather than just hair. Whoa. But these are so these are like the first example of like a non-spherical microplex. And yeah, it was what I wanted to work on. It's why I joined like the Manners group and got my EPSRC fellowship. And so it was really satisfying to see that project through from like thinking about it as an idea and what I wanted to work on to like actually achieving something and like publishing with it. So I think that was probably my favorite thing that I've done.
I can imagine why you picked this one. This sounds so cool. That is so cool. So maybe we can tweak the analogy a little bit and say that with this hairbrush, what gets stuck is not hair, but it's what gets stuck is maybe some oil or some nourishment for the hair, and then you use that to. I mean,
Yeah.
you're not the hair, but yeah, well,
Yeah.
that sounds so cool. And what were these sticks made out of? This block polymer that you mentioned earlier?
Yeah.
Ah,
It's a block copolymer. So the process by which we make these particles, these like sticks, is called crystallization-driven self-assembly, which is quite a complicated sentence. But what it literally means is that there are different driving forces for making the polymers come together into like a nanoparticle. And in
Right.
CDSA, if you have a polymer that can crystallize with a core forming block, so if the backbone of the hairbrush is something that could crystallize, then as that crystallizes, that like favors the formation of one-dimensional structures. And so the system I made, I sort of used a bunch of sort of like off-the-shelf components from different fields. So I took a crystallizable core-forming polymer that had been shown to crystallize and self-assemble into nanofibers, into like tiny sticks. And then I took a polymer that had been widely studied in gene delivery, which is called like PDMA, EMA. But yeah, it's this polymer, and people have shown that this polymer can bind to DNA and take it inside a cell. But the way most people do that is just mixing polymer and DNA without having them being in any nanostructures. And if you do that, it makes what's called a polyplex, which is literally like a bundle. It's like if you have like a drawer full of cables that you haven't touched and they all intertwine and get tangled up together. That's literally what it looks like. So imagine like a nano-sized ball of wool that has two different types of wool in it. So that's what like normal polymers do. So I took the polymer that can bind DNA and then added it to the polymer that can crystallize, and then that enabled me to get like the one-dimensional like tiny sticks that were able to actually bind DNA onto the outside and retain some control over their size and shape.
Okay, that sounds really cool. So can we say that because I'm going in the direction of using the nanosticks to deliver medicines, so can we say what is this magic brush that the witches have that they fly on, or in Harry Potter, you know what I mean?
Yeah,
Brushes that
like the
fly around.
like the broom, like the Nimbus 2000, and
Exactly, the Nimbus 2000. Um, but in this case, in your case, it's like the witches are actually gonna cure your cancer potentially, or they're gonna cure any. Is it only for cancer or any drug delivery?
So this is something I want to study next, and this is because it's kind of like a platform. So you could in theory bind any nucleic acid, so any DNA or RNA medicine could be delivered, and it's sort of like a modular system. So what we hope to be able to do is to adapt it to target different locations in the body and different diseases, and then deliver different types of medicine. So I just worked with I made glow in the dark brain cancer cells, basically. So I delivered a DNA sequence for what's called like firefly luciferase, which is it's the thing that makes fireflies glow in the dark. It's a protein, and it's a good way of testing how well your delivery systems work, because how much the cells glow is directly related to how much you delivered, how much medicine you delivered.
Wow, please tell me you have pictures and videos. Please tell me.
So I've got pictures of I've got some pictures of the cells and stuff.
Oh my God, that sounds so cool. That sounds so cool. Okay, so okay, I'm thinking like nano brooms for witches who are drunk. No, that's too long. Let's talk about it later. Okay, so Steve, what is clear to me is that you love the research aspect of being a scientist. I mean, that was one of the reasons why you chose chemistry over computer science. Because there is no liquid nitrogen in computer science. There is nothing, no chemicals really like happening there. So, but what else do you like? Especially because you're a postdoc, so you're not a student anymore. So what else do you like about being a scientist?
I think primarily the freedom, and this like has a number of benefits. So one of them is that I'm pushed to the limits of what I can achieve. There's the only limit to what I do is like what my own brain is capable of, which is I think it's very rare for a job to push your brain to the limits of what it can do. So like every day my brain gets a really good like mental workout, and I think that's something that is not as present in other careers. And I think it's something that scientists are quite lucky. I like the freedom to choose your own research directions, and you get to pick any area and something that you find fascinating and work on it. So I transitioned from making sort of like small molecule sugars that was like designed as anti-cancer drugs to delivering to like making like polymer nanoparticles, which is a very different field. But I was interested in it, and I moved there, and I've started studying it, which is something I really enjoy. And I like the freedom of like the work-life balance. So it depends on like what groups you're in and what universities you're in. But my supervisor's quite like laid back, and so we get to choose our own working hours. We get to choose like when we want to work and for how long we want to work. And I like the freedom of that kind of the work-life balance is better in that respect.
So the mental gym and the work-life balance.
Yeah.
And freedom.
Yeah. I also really like meeting people as a scientist, you get to meet people from all walks of life and every place imaginable. And I really enjoy meeting other people that have lived very different lives to yourself, and talking to them and seeing, science is like a utopia in that sort of way. You have like people from all over the world coming together to like advance humanity in some way, which is one of the things I think is like really cool.
Yeah, absolutely. I agree. And honestly, I have to say that it's a bit of an unusual thing, because usually academia, at least in most parts of the world, is not known to offer work-life balance. Let's put it that way. That's of course because of the broken systems and broken institutions, so on and so forth. So I'm very happy that you're in a place where you get the freedom to have your own working hours, because I think research or being a scientist is also a very creative process, and you can't just be like, okay, from 9 to 6 you have to be in the lab and you have to because the freer you are, the more free you are, the more creative and more productive you will be. So it's basically actually helping the employer get the best talent out of you. Absolutely. That makes sense. And how's the campus like? Is there like a lake, or is there like trees? Like, I mean, not right now, probably because it's winter. But is it like a beautiful campus, or is it just like a?
Yeah, it's a beautiful campus with some. I think it's unfortunate that a lot of the buildings were built in the 60s, so they're quite like the architecture is not as great. I don't think the architecture does the campus justice, because the campus itself is beautiful. We've got like so there's big green spaces, lovely trees and forests. There's like a botanical garden on campus. We're also about like a 10 to 15-minute walk from the beach. There's this like beautiful bay called Cabra Bay, and you can see the Olympic. So like we're on an island, and south of the island is the Olympic mountain range, which is near Seattle. So basically, if you look across the water, you can see the Olympic mountains, and there's like if you look across the east side of the island, there's the Cascades, which are run near Vancouver. So the backdrop, wherever you look, is like mountain ranges, basically, which is really, really beautiful. Yeah, the campus is really beautiful.
I need to visit you. I have this strong urge, this feeling that I need to visit you, because you're 10-15 minutes walk from the beach? What the hell, dude? What the hell? Wow.
It's so good. And also, people think the weather is really bad in Canada, but in Victoria, like sometimes in summertime, it's 20 degrees, sunshine, blue sky from about May till the end of September. So you can go. It's like much more consistent than you would think. Yeah, my boss is from the UK, and he, as a scientist, he analyzed the weather patterns from the UK and Victoria, and it rains the same. It just rains in winter in Victoria, and then the summertime is like just sunshine and actually nice weather, which is something that's quite rare for me, but I really enjoy.
Okay, I'm going to ask you questions about moving to Victoria, because I'm convinced. I'm looking for a place which is close to the beach, which has decent work-life balance. and everything. Victoria is just ticking all the boxes for me. I need to look into the migration part of that for sure. All right, that's awesome. So it's. I mean, it sounds like your research experience has been wonderful. I mean, your research took you from the UK to Victoria to this dreamland. In my head, it is a dreamland. However, if you would like to improve your research experience, and you had three wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
Okay. I think the first thing is to have streamlined the way people get funding to do science, because I think this is one of the most fundamental problems, is that
Yes.
there's only so many opportunities, and happens at every stage that you do science. So whether you're like a PhD student, a postdoc, a young academic, or a senior academic, or you always have to compete for the same fellowships and funding opportunities, and they are so like in demand. The chances of success is really, really low. And what this means is that ultimately, like, you have a situation, and the amount of work required to get them is significant. There's a lot of work that goes into, especially to have an application that stands a chance of being successful in such a competitive environment, requires weeks or months of your time. And you have a situation where like the success rate is below 1% or something. And so you think about, like, you have thousands of scientists spending weeks and months of their time writing proposals for what they would like to do, which will ultimately just be rejected, and they won't get the money to do it. And that's just so wasteful, because they also have to pay, or they have to find scientists to review the grant applications as well. So it's just a monumental waste of time and money. And you think about what those thousands of scientists could do with several months of time if they didn't spend it like wasting it writing applications. So I think that's one area. And I think I read something a while ago about, I think it was like in Australia, they did a study and they found out that the amount of it cost more money to administer the like Australian grant system than the money they were giving out. So like there was actually like, it would have been better for them to just give the money out randomly to people or whatever, because they would have had more money. The taxpayers would have had more money left in the bank afterwards, which is like a pretty crazy situation. So I think that's one thing I would definitely like to change.
Better funding system, research grants and funding system. Yeah, definitely. Okay, two more. Go.
And then the second one is, I think, a better. This is sort of. It doesn't immediately sound like it's related to research, but I think it is, and it's to get people to understand chemistry and like science better, because I think a lot of normally when you say you're a chemist to people, they have the same. There's a couple of reactions that you get, and the first one is just a look of confusion and then like visible pain on their face, and then they just say, "Oh, I was never any good at chemistry," or like, "Oh, I didn't like chemistry at school," or something, and like they just glaze over as they relive the horrors of like their like high school or secondary school like science, and but it's a really important discipline that has like there's lots of problems the world faces today that are in the realms of chemistry that need to be solved, and it impacts people that study chemistry further. So I think it's kind of misunderstood, and that's why people don't study it more, which impacts, for example, because they don't study it as an undergraduate, they don't study it for a PhD, which means that they don't go on to be a postdoc, they don't go on to become like a faculty. And I think it means that sort of like chemistry is lacking a diversity of people that have been turned away from science. So I think it would be nice to correct that and have the public understand chemistry a bit better and have a more diverse representative group of people doing science. I think that'd be number two.
Yeah, absolutely. Yeah, that makes sense. Did Breaking Bad help? What do you think?
So I think it did, because honestly it made chemistry seem cool, and people now they appreciate it a lot more. So I think it did. It is good. It's good. The side effect is that everybody thinks now as chemists we're like in the desert in a Winnebago, like cooking crystal meth or something. So that's like
Isn't that what you're doing on all those ferry rides that you go on? Like
so many ferry rides. Yeah.
All right, that's a fair wish. Yeah, that's number two. Last one. Be wise.
Okay. And the last one is that like I would like a better quality of life for scientists in academia. So academia normally has less money than, for example, industry and other business, and especially under other industries. So this means that like you look at your friends and that are doing other things. Like they might have, for example, I consider computer science. They might have actually gone on to study computer science, and they have things like private healthcare. Like their work is like a nice building that's modern. They have like spaces to relax and socialize. They have complimentary tea and coffee and drinks and like snacks, and like they might have a gym membership included in their like work, and like all these kinds of things are missing in academia. Academia is sort of like a building that was built in the 60s with like equipment that varies depending on exactly where you're studying it, and there's not normally any of these sort of like nice to haves. So I think it would be nice if academia was more like a Silicon Valley tech startup or something, where there was like cool stuff happening that made like your life at work more enjoyable.
Yeah, that makes sense. Yeah, that makes sense. I mean, you did mention the word that you do have work-life balance, but it is nothing compared to a job at corporate. It is amazing compared to other academia jobs or other situations, whatever, but it's nothing compared to a Silicon Valley startup. So I totally am with you. Like you put it exactly like perfectly, like built in the 60s, maybe some equipment here or there, and but yeah, it would definitely I think it's important to make research and academia more lucrative, so that also to attract more bright minds. I mean, duh. Yeah. I agree. I agree. But hey, all three of your wishes, at least the second one, which is that people understand chemistry better, you're already doing that. You're part of this. You are taking over the Real Scientist Nano Twitter account, and you are on the podcast. And I hope even if it inspires one person to be like, oh yeah, chemistry is actually really cool, and next time I'm gonna maybe pursue chemistry or encourage someone else to pursue chemistry, I think our job is done. And yeah, with number one, like with the research funding process, I mean, all I can say is that I'm glad we have people like you who have identified, who are not denying that things need to change, who are not in denial, but you are in the process. Let's put it like you're thinking about it. You're actively. You don't have answers right now, but first step towards solving a problem is to acknowledge that there is a problem. So I think next time when you're on the podcast, hopefully things are slightly better. So let's go from 1% to 2%, or well, fuck it, let's go to 50%. University of Victoria starts giving out gym membership, or at least free coffee and very important. I mean, without coffee and tea, I don't know where science will be. I mean, come on, this is like basics. Absolutely, I agree. Well, I hope all your wishes come true. I really, really hope so. And this has been wonderful, Steve. But before I let you go, what can the followers expect when you're taking over the Real Scientist Nano Twitter account?
Okay, that's a good question. So I think I want to sort of introduce myself and the decisions I made to get me to where I am today, to hopefully help people with their own, whatever stage of their own careers and decisions they're making are at. They can hopefully get a diversity of like experiences from other people. I want to sort of introduce my research area more generally and why it's important, like why we should care about nanomaterials, and the challenge, where the field is at, like the challenges and the opportunities in nanomedicine and with nanomaterials, and then talk about like my own research bit and sort of how that hopefully fits into the addressing the challenges and trying to optimize the opportunities that are available. And then I was thinking about doing maybe like a question and answer session towards the end where people could sort of like ask any questions that they wanted, and then I could give them like an honest answer. And then maybe just sort of some future, what do I think the future holds for like myself and for the field and that sort of thing.
Okay, and a nice mixture of beach pictures and campus pictures and attracting more tourists to Victoria, and the fair pictures and all of that as well, I hope.
Yeah, definitely. I'm definitely going to weave in some photos of Victoria, British Columbia, and my day-to-day life as we go throughout the week.
Okay, perfect. That sounds great. Thank you very much, Steve. This has been wonderful, and really excited and looking forward to having you on Real Scientist Nano. Thank you for speaking with me.
Awesome. Thanks for having me.